And yeah, so I don't know what, especially younger people know, so please ask any questions you would like to ask. So I start with some basic notations. Well, so X will always be an n-dimensional projective variety. Normal. But for many things, you can just think about of a projective manifold. Yeah, it doesn't matter. And then I have my wife was calling something. So I have a locally free sheaf. And I say that E is ample. If and only if you take the projectilization of E and then the O of 1 on that, and I assume that this is ample. So this is a line bundle on another projective variety, and I assume that this is ample. And I see that, and I say that E is Nef, if and only if OPE of 1 is Nef. Sometimes I call this just theta. And Nef means that theta times C is non-negative for all terms in here. So you can test this also on the curves downstairs. And I should also say that this notion extends to sheaves. It's not the same definition. Extends to any coherent sheaves. This will appear maybe in the last talk. And in this case, well, one has to be very careful if you take projectivization of a coherent sheaf. I mean, in the locally free case, you just, if you have a rank R bundle, you get a PR minus 1 bundle over X. But here, some fibers could have larger dimension. Yeah? And in particular, this variety might not be irreducible. So one has to be very careful about that. Can be terrible. But anyway, many properties of these coherent sheaves are the same as for locally free sheaves. There's a nice paper by Vincenzo Ancona on ample faisceau ample, something like that, where you can find these properties. But mostly you can just think about locally free sheaves. And then there's one important notion that E is generically Nef. If and only if the following holds. For all ample line bundles. And for curves, how should I write this? E1 times En1 1, where the dj are in Mj, in the linear system Mj Hk, where Mj are sufficiently large. Yeah, so you take hyperplane sections in some ample line bundles of sufficiently large degree. If you have this one, then E, so E is locally free, say. Then E restricted to this one is Nef. Okay, So it's not nef on every curve, but on sufficiently general curves, so to speak. And even if you are on a normal variety, if you cut down here, then this will automatically be in the smooth locus of X, yeah, because the singularities of this one are in codimension 2. Yeah.
See. Why? Do this.
It's very general. Yeah, so the dj should be general. Yeah, and then you get a smooth curve. So in some sense, you take hyperplane sections of sufficiently large degree, but I mean, you can also change the ample line bundle. So maybe I should not use this one. The basic question is, yeah, okay. So now I will assume that the Kodaira dimension of X is non-negative. So this means that there is some number M such that you can find a section in NKX. And yeah, I should say that in many theorems, like I will just write down the theorem of Miyaoka, there's a geometric interpretation of this, this condition here. So the conjecture is that the Kodaira dimension of X is non-negative if and only if X is univocal. Is not uniruled. Is not uniruled, which means, so the definition is that X is not covered by rational terms. And this is known in dimension up to 3. And yeah, I think in higher dimensions, this is one of the leading conjectures in well, at least in this global theory of algebraic geometry, so-called non-vanishing conjecture. But I don't want to speak much about this.
Is the conjecture easier if you assume Kodaira positive?
Well, I think maybe I should make a remark. If the Kodaira dimension is non-negative, then X is not mediate. So why? So one direction is clear. Because, so if X is uniruled, and if you take a family CT of rational curves covering X, then the canonical bundle times CT will not be. So let's assume smooth. Yeah? And the canonical bundle on these rational curves will be negative. So no multiple of the canonical divisor can have a section. Yeah? Yeah, if you have this property, then of course it follows that the Kodaira state these cannot have sections like that. Okay. And so to speak, the conjecture is that if X is not uni-ruled, or if X is uni-ruled, then the Kodaira dimension should be minus infinity. Yeah? And this is, yeah, in dimension at least 4, it's completely open. Though there are some cases known, but I think in general, people don't know how to do this. Okay, so I will concentrate on these manifolds with Kodaira dimension non-negative and equivalently not covered by rational curves. The question is, so how positive is the sheaf of holomorphic one forms, of the vector bundle of holomorphic one forms? So say X smooth. And sometimes I abbreviate stress by omega X. So, yeah, so the canonical bundle has some positivity. Yeah.
Yeah.
And now you ask, what happens to the cotangent bundle? And then there is a theorem of Miyaoka from the 80s. So X is a normal projective variety. It is not uni-ruled. Then, if you want X smooth, then omega X is generically net. Yeah, so if omega X is not generically nef, Miyaoka constructed a family of rational curves. So this goes via characteristic P. And X, it doesn't make really sense, it doesn't make problems to say that X is normal, because we restrict to a very general curve, and the very general curve will live in the smooth locus. So you don't care about omega X is locally free everywhere, just suffices, of course, that omega X is locally free on the smooth locus, which is clear. Yeah, so okay. Yeah, and there's a vast generalization by Campana-Pound, which I probably will mention later. Okay. So I think if you don't make any more assumptions on X, you cannot say really much more about the positivity, because you can blow up and blow down and things, and that this destroys a lot of things. Yeah. So let's look at some examples before I proceed. So now I want to discuss whether omega X, the sheaf of holomorphic one forms, is nef or not, things like that. Yeah. Okay. So let's look at very simple examples. So I take a Calabi-Yau manifold. Say that so the canonical bundle is trivial. And say that the fundamental to simply connected. So in this case, omega X cannot be nef. Okay, why not? Can you, if I use this line, can you still, yeah? So I have a general remark. if E is an F locally free, then the first Chern class E times any ample line bundles is always larger than C2 times the product of this line bundles. I think I should spare. Yeah. So if now, if the canonical bundle is trivial, of course, then C1 squared is 0. So then it follows that C2 of x times H1 to Hn minus 1, n minus 2 is 0, which means that C2 of x is exactly 0. So this is a class sitting in H4. Yeah, so you have a projective manifold with trivial canonical class, and the second Chern class is 0. And then there's a big theorem by Yao, using Kähler-Einstein matrix, saying that there is a finite A-type cover such that X tilde is a torus. Of course, this is not possible since X is simply connected. And actually, I don't know an easy argument without Yao to prove this. I mean, you can easily generalize that. So using this Bogomolov decomposition, get the following. Maybe this was the example, it was 1.3. Yeah, okay. So if you have a projective manifold, the first Chern class is 0 in H2XR. Omega X is nef. So the Bogomolov decomposition decomposes after finite A-type cover the manifold in, so to speak, simply connected part and a torus part. So you just the same argument using this decomposition gives the finite A-type cover. C2 of finite A-type cover. And it's Kähler equals actually abelian, of course, because we are just in the algebraic setting, but this would also work in the for Kähler manifolds. And there's also a simpler version also called KLT varieties, but I think at the moment I will put that in. It's of course what happens if omega x, if the Kodaira dimension gets larger. So this was, so to speak, the case where the Kodaira dimension is 0. And of course, I mean, so maybe we first have a look at the case where the cotangent bundle is ample. Okay. So the case where the cotangent bundle is ample. By same thing as for this Neff vector bundle here, you have the third class inequality. C1 squared is larger than C2 of x. So this means that you, if you dot it with H1 up to Hn minus 2, yeah, nice term class inequality. You also know that the canonical bundle, of course, is ample. It is determinate. And then we know that X is scalar Einstein. And what else do I want to say? And then omega X is semi-stable with respect to the canonical bundle. I will come to this in the third lecture. And then you have the so-called Miyaoka-Yau inequality, namely that, so X was n-dimensional, right? So C1 squared of X times Kx to the n minus 2 is less or equal, I always get the numbers wrong. You have this inequality. Okay. So I will come back to this inequality in the third lecture. Okay, so we have a lot of nice, so to speak, consequences of this ampleness. And then, of course, the question is, what examples do you have for ample cotangent bundle? A lot of people spend a lot of energy computing this. And I will just recall some examples. So the first example is so X is of course always V. Yeah? So suppose that the universal cover X is the ball. Yeah, so you look at the universal cover and you assume that's the ball, and then there's a classical theory saying that omega x is ample. And this is 60s or so, 70s, the Kobayashi. So here you look at the Bergman metric. The special metric here on the ball, and this descends, to x and gives something called metric on x, gives a negative bisection. So So this is a very differential geometric argument. Of course, the universal cover is something complex analytic, yeah? I mean, it's clear that you need some differential geometric argument, and the negative bisexual curvature implies that the cotangent bundle is ample. And so this is, so to speak, the differential geometric version of ampleness of the cotangent bundle. So this is a very classical thing. Another example, a counterexample. So suppose that omega x is ample. So you want to make more examples, then of course the easiest thing would be to take the product, yeah? So omega x is less than, but never ample. Yeah, so
Sorry.
hmm?
You want to take some product?
Oh, sorry. Sorry, yes. So why? Yeah, because this is simply the product of omega x on the first factor plus the product of omega x on the second factor. And then, of course, if it would be ample, then this would be ample, and this would be ample, which is certainly not true because it's trivial on the fibers. Yeah? Okay. So one has to be very cautious. It's not so easy to make examples where the cotangent bundles. Then, of course, let's see. Many examples by Xie, Taranto, and many others. If x in Pn is a complete intersection general complete intersection. What else? The need of large degree. I think you need that the code dimension of x is larger than the dimension of x, then omega x. And I don't want to make to be here more precise, but you just look at the papers of Mamiya and other people, because it's rather technical to state that. Yeah, so if you take a sufficiently nice complete intersection in projective space, you get a lot of examples. I think because of this example here, there was some time where people believed that the cotangent bundle ample implies that pi1 cannot be 0. Yeah, so no, but this was, I mean, these are, for instance, counterexamples. Yeah? I mean, this is not true. Even for surfaces, we can construct examples. Okay. Okay, so now I come really to the point of intermediate Kodaira dimension. Yeah. So I don't want to assume ampleness, and I don't want to assume that the canonical bundle is very trivial. But I would want to look at the intermediate case. And there's a following conjecture by Wu and Chang. 2002. I think probably they are not uniquely determined, but just. So we take a projective manifold and you assume omega x is left. Then there should be a finite eta cover. Such that eta vibration is smooth. Y tilde is a projective manifold. The canonical bundle of Y tilde is ample. And all fibers of phi tilde, let me see. Fibers. Phi tilde are tori. So this is, so to speak, the picture between the ample case, and the case where the canonical bundle is trivial. No? Canonical bundle is trivial, for numerical trivial, then Y tilde would be a point and X tilde would be just a torus. Smooth means that all fibers are manifolds. Yeah. And the eta K vibration, what's the eta K vibration? So this is given by sections in the canonical bundle. So I think at the end, the canonical bundle, some multiple of the canonical bundle is generated by global sections, and then gives you the eta K vibration, and this eta K vibration is actually smooth.
For M large enough.
For M large enough. There exists some M. Yeah. Eta K vibration smooth with connected fibers. Of course, if you take them to multiples of M, that would also be do the job. Okay. Yeah, it would be nice to. Maybe I can take a conjecture here once more, just for the audience. For the conjecture is omega x naught, and that is I have like smooth forward vibration. The boundary of that is simple. And that's yeah.
Just a question. So it does one explain also omega 1, why it did that be that? Or instead of yes?
This is not so clear to me. But probably, I think one should expect maybe a little bit more. Yeah, it would be nice to discuss that.
Also, in the case of omega x math, x can be of maximal Kodaira dimension, right?
Well, Y tilde could be, I mean, this could be an isomorphism, of course.
Yeah, make the product of two curves.
Yes.
Yeah. Yeah.
Yes.
Yeah.
Okay.
Just a lesson.
I mean, omega x could be nef and big. So this is, I think, some point which will be discussed also a bit.
And in that conjecture, what is the more conjecture part? In that conjecture, on the conclusion, what's the hardest part?
Well, what's completely unclear is whether you have really a Ithaka vibration. I mean, abundance is, so to speak, included in that. Yeah? So I will now discuss the solution of this conjecture in two special cases, and then you will see what's going on.
So if abundance is achieved, is it triggered?
If abundance is assumed, then this is true. So yeah. This is what I want to explain next. This is the theorem by Höring in 2011, I think. So Kx, I assume now Kx is semi-ample. So this means that this is generated by global sections. Or something. Then conjecture holds. Yes, so you see that Kx nef is our general assumption. If Kx is nef, then abundance conjecture says that, well, I mentioned the non-vanishing theorem before. Non-vanishing conjecture says that if Kx is nef, then should have a second. But abundance says much more, namely that if Kx is nef, then some multiple should be generated by global sections. And then you get a nice holomorphic Ithaka vibration. But this is, abundance conjecture is known in up to dimension 3, but starting from dimension 4, completely open. So the theorem of Höring says if the abundance conjecture is true, then this conjecture is true. And since everybody believes in the abundance conjecture, so this gives a strong hint that also this conjecture should be true. So it's just some kind of test case. Okay. So I would like now to give an idea of the proof. So we know that MKX is spanned in global sections. So then we get this Ithaka vibration. So this has connected fibers by definition. And yeah. So to speak, the property of the Ithaka vibration is that the canonical bundle is, so to speak, numerically trivial on the fibers of phi. So I formulated this, well, canonical bundle is relatively numerically trivial. I can also put a minus here. Okay, so now omega x is nef. And we look now at the tangent bundle. The tangent bundle is lambda n omega 1x tensor the. How do I want to say this? So this is a formula from linear algebra. The tangent bundle is the n minus first wedge power of the cotangent bundle times minus kx. So this is nef. So this is phi numerically trivial. So the tangent bundle is phi numerically trivial. Nef, trivial, doesn't matter. Actually trivial. Yeah. So the tangent bundle has some flatness property or nefness property with respect to some morphism. And then there's an old theorem by Peternell, Schneider, and myself, which was reformulated by Höring, Wiśniewski. So this implies that phi is actually it's equidimensional and much better in almost smooth. Almost smooth means that the reduction of all fibers are smooth. Any fiber is smooth. Some fibers could have multiplicities. Yeah. So let me somehow give some hint why this is true. So say F is a reduced singular irreducible fiber of this point. Just to make some example. Point of L1. Then I look at the cotangent sequence. Here I have omega x respective to f, so this is now a flat bundle. And here I have omega f. The conormal of the fiber has a tendency to be positive. For instance, if the dimension of the fiber is larger than the expected dimension, yeah, so then you get sections here in the cotangent, which go to sections here. The sections here will have zeros, and this is a contradiction to the flatness. Yeah, so here you have positivity. If the fiber is, so to speak, has too large dimension, you have too much positivity here, which gives positivity here, which cannot happen. So then you see that F has dimension, the expected dimension, from x minus from y, and then you get here a zero, basically. Yeah, and then, so this is a nice fiber, so the dimension D. So this will be a triple sheaf of dimension D, and the conormal bundle will be trivial. Yeah, so that's what you expect, of course. And if the conormal bundles here is trivial, you have a map from a trivial bundle to a flat bundle. This must be a subbundle. Yeah? You cannot have, in a flat bundle, you cannot have sections which don't vanish, which vanish at some point. Yeah? So that's not possible. Yeah, everything is, so to speak, trivial. You may think of here, you have a trivial sheaf. So this means that this here is a subbundle. But if this is subbundle, then this is locally free. And if omega f is locally free, this means, of course, that f is unique. And actually it holds. Here I neglected a lot of technical details, yeah? But this is just the philosophy one proof works. Okay, so now see. Now you look at the eta calibration. So for details, you can easily look at Hörich's paper. Yeah? Eta calibration is now almost smooth. And then standard techniques say that you can find an finite eta cover. You have to ramify here over y. And the induced thing is smooth eta calibration. So you can remove, so to speak, this disadvantage of having multiple fibers by going to some finite eta cover. Yeah, okay. But still, we want to prove that the canonical bundle is ample. Here, Höring has to rely on some result of Kodaira. I mean, eta calibration on general fiber, all fibers are tolerant. We already know that. Kodaira proved that actually phi tilde is an abelian group scheme. Which means that phi tilde is a section. So this is proved in this famous paper of Kodaira on the Shafarevich net. Yeah? Here you have to really put in some information. So we have a section. So a section means that you have a map here, you have its subvariety S in X tilde, and you have a map to Y tilde, which is an isomorphism. Okay, and now we want to prove that the canonical bundle of Y tilde is ample. Yeah? So we know, of course, because we have eta calibration, that the canonical bundle of Y tilde is the same as the canonical bundle of Y tilde and X tilde are the same. And now, so assume Y tilde is not ample. So then there exists a rational curve C in Y tilde. We'll explain this in 1 second. we have a section. Now we have a section here, and we have a rational curve here. So we have a rational curve in S. So this is a contradiction to omega x is nef. Why? Nef implies that there is no rational curve in X. So why? Yeah. If C is a rational curve, then you look at denormalization. Then you have a map from the tangent bundle of P1 to the correct at the tangent bundle of X. No? Or in other words, you have a map from omega x to C to omega 1 P1. So, but this is nef, and this is O of minus 2. So this is of course not possible.
Here, access.
F,
Omega x to that.
yeah. No, I think I changed notation, so to speak. Oh, this is a lemma. Yeah, but of course I apply it to X tilde. Okay, and then, yes, I also have to explain that if ky at this point that if ky tilde is not ample, then there is a rational curve. So let's first assume that if ky tilde is not nef. If it would be not nef, then there's this big theorem of Mori. Characters would be, yeah? With k tilde times p is negative. Okay, in this case we are done. No? So yeah. So we may assume that ky tilde is nef. But we also know that the Kodaira dimension is maximal. This was the Ithaca configuration. So this means that ky tilde is not only nef, but it's also big. So it's big and nef. And then yeah, in this case, the base point theorem says that m chi is standing by global sections. So then we get a morphism phi from y tilde to some sec tilde, bi-rational. And k, so to speak, ky tilde here is zero on the fibers. But then Kawamata has shown that psi contracts rational first. Yeah. So think about a surface of general type where the canonical is big and nef. Then this map would contract the -2 curves. Yeah. And Kawamata theorem is, so to speak, the generalization of this.
So maybe a nice question. What about if ky tilde is nef but not ample?
If it's nef and not ample, then
But your first point say in that case, you can still find a rational curve in y.
so if it is not nef, then I apply Morris theory and I find a rational curve. So I may assume that the canonical bundle is nef.
Yes. Can reduce to benefit by using.
So the upshot is if ky tilde is not ample and it's of general type, you always find rational curve. Okay. Yeah. So maybe in the last 2 minutes, I want to state the other theorem. Concerning this conjecture. By EY Matsuura, which is a thing in the archive. It's not yet appeared. So it says the following. So if a projective manifold, we assume Kx is nef. Actually, Kodaira is sufficient. Then the second rank class to be 0 is equivalent to saying that omega x is nef and the numerical dimension is 0 or 1. So the numerical dimension is that this one is not numerically trivial, but the canonical to the power n minus the first term class, yeah? Maybe 8. First term class of kx to mu is non-zero, and the first term class of x to mu x1 is 0. And the second assertion is if omega x is nef and mu is 0 or 1, then kx is invariant. And then Höring applies. Semi-ample means that some multiple is spent. Okay. So one direction here we just saw, if omega x is nef and C2 is 0, if omega 1x is here, this one, and this is 0, then C2 of x is 0. So this was Yao. And so maybe this was the last remark. In A, sorry, in the A and B,
If omega x was.
This nef, sorry. If you have nefness here, yeah, if you're in this situation, then kx is imium, and then you are in a nice situation. Maybe my last remark here, if nu is 1, then nefness, but this is very easy. C1 squared times h to the n minus 2 is larger equal to 2 of x times larger equal to 2. And so this is 0 because the numerical dimension is 1. So this implies that this is 0 for all h, and then CQ of x is 0, and then you are. Okay. And yeah, I think my time is over. If there's some interest, I can still explain the proof in one of the next 2 talks. I would have to rearrange, but I mean, it depends on the audience. Okay, I think I will stop here.
How much time is that? Will you do it now?
No, I think I would need 15 minutes or so. But I could easily integrate it in the next talk.
Okay. Are there any questions? Well, since we